Welcome to sections 6.2 and 6.3, more examples of how to solve trigonometric equations and trigonometric equations involving multiple angles. So we're going to look at a few more advanced techniques that are needed for solving other kinds of trigonometric equations. Example 1 asks us to find all solutions of each equation on the interval from 0 to 2 pi. So example A, we have tangent of 2x minus rad 3 is equal to 0. Okay, so we'll begin this problem just like we did in the last section, section 6.1. Make sure you are comfortable, you've watched that video and done the homework assignment before you move on to this section. So we're going to isolate the trig function, so I'm going to write tangent of 2x is equal to rad 3. And then in this case, notice something that's a little different than the previous problems. We're asked to find solutions only on the interval from 0 to 2 pi. However, the argument here is 2x, not just x. And let's think about what that means when we were graphing back in the previous chapter. We know that when there's a coefficient in front of the argument, that affects the period of the graph. And in this case, since it's a 2x, then that would take the period and cut it in half. So this being the case, we're going to have more solutions than typical on a unit circle to the equation because basically tangent of 2x is repeating twice as much as tangent of x would. So how to proceed? Well, there's several different techniques. One thing that I like to do is I treat this as if I was solving and finding all possible solutions, not just the ones on 0 to 2 pi. So what I mean by that is you would say, okay, 2x is going to be equal to, so let's think, when is tangent equal to rad 3? Well, that would be when sine is rad 3 over 2 and cosine is 1/2, so at a pi over 3 reference angle. So I'm just going to write 2x equals pi over 3 plus pi times k, right? Since the period on tangent is pi, and so at pi over 3 as well as 4 pi over 3, so on and so forth, I'm going to have solutions to this equation. Now you might say, but wait a minute, it's only asking for solutions from 0 to 2 pi. We're going to get there in just a second. So now I'm going to isolate x. I'm going to divide the whole equation through by 2. So then that means x would equal pi over 3 divided by 2 is going to become pi over 6. Plus, and then dividing pi k by 2, I have pi over 2 times k. All right. Now what we do is we're going to plug in different values of k. Remember, k can be any integer, and generate all possible solutions, all possible x values that fall within the interval from 0 to 2 pi. So here's what I mean. If k is equal to 0, then that means x would equal pi over 6 plus pi over 2 times 0. So that would just be pi over 6. If k is 1, then that means x is pi over 6 plus pi over 2 times 1. So pi over 6 plus pi over 2 is 3 pi over 6 plus pi over 6, that's 4 pi over 6, so that's 2 pi over 3. That's still within 0 to 2 pi. If k is equal to 2, then x is equal to pi over 6 plus pi over 2 times 2, so that's plus pi, so this would be 7 pi over 6. Is that still within the interval from 0 to 2 pi? You bet. And then let's see, if k is equal to 3, then that means x is equal to pi over 6 plus 3 pi over 2, which is 9 pi over 6, plus pi over 6, that's 10 pi over 6, so that's 5 pi over 3. And then if k is equal to 4, then that's too big, because then that would mean x is pi over 6 plus 4 times pi over 2 is 2 pi, but that's outside of the interval from 0 to 2 pi, right? That's going to be bigger than 2 pi, so we stop there. So these are the only solutions that fall within the interval from 0 to 2 pi. So those will go in the solution set. Pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. That's our final answer. Notice we had how many solutions? We had 4. If you just listed where tangent was equal to rad 3, you would only have gotten 2 of the solutions. You'd be missing the other 2. You'd be missing half of them because remember the period was cut in half, so we have double the number of solutions. All right, moving on to another example. Let's draw a little line here so we can separate the problems. So we have 2 cosine 2x is equal to rad 3. So same as last time, we're going to get started by isolating the trig function. So I have cosine of 2x equals rad 3 over 2. And then again, see how we have a coefficient in front of the argument here? So I'm just going to list out the general solution as if we were going to be giving all possible, and then I'll list out which ones fall within 0 to 2 pi. So let's think, when is cosine equal to rad 3 over 2? Well, 2x would equal pi over 6 plus 2 pi k. Would that capture all my solutions? No, also in quadrant 4, cosine's positive. So, or 2x is equal to, that would be 11 pi over 6 plus 2 pi k. All right, now dividing each of these equations by 2, I get x equals pi over 12 plus pi k, or x equals 11 pi over 12 plus pi k. Now from here, we're going to plug in values of k so that we can get all possible solutions, all possible values of x that fall within 0 to 2 pi. So looking at this first equation here, if k is 0, then I just get pi over 12. And if k is 1, pi over 12 plus pi, that's going to be 13 pi over 12. I stopped there because if k is 2, that's already adding 2 pi to pi over 12. That's going to be bigger than 2 pi. Now over here, if k is 0, here I'll list out. This was for k equals 0. This is for k equals 1. So if k is 0, I have 11 pi over 12. And then if k is 1, which is 12 pi over 12, then 12 plus 11 gives me 23 pi over 12. And that's it. So here are my 4 solutions again. Pi over 12, 13 pi over 12, 11 pi over 12, and 23 pi over 12. All right. Nice. Okay, next one. Here, let's separate these. 2 sine of theta over 2 plus 1 equals 0. So to start, I'll isolate sine of theta over 2. So I have 2 sine theta over 2 is negative 1. So sine of theta over 2 equals negative 1/2. Okay. Now in this case, the period's actually being doubled, so you don't have to worry about having more solutions. But if you just want to do the same procedure for all the problems, it'll work out just fine. So I'll proceed that way, even though we don't have to worry in this case. Okay, so let's think, when is sine equal to negative 1/2? Well, we have 2 cases. So either, let's see here, theta over 2. So sine's negative in quadrants 3 and 4, right? So theta over 2 would be 7 pi over 6 plus 2 pi k, or theta over 2, here's the other case, quadrant 4, is 11 pi over 6 plus 2 pi k. And then here you'll see why we don't really need to worry about picking up extra solutions, because I'm going to multiply everything through by 2 this time, right? So theta would equal, multiplying 7 pi over 6 by 2, it's going to become 7 pi over 3 plus 4 pi k, or theta over 2 equals 11 pi over 3 plus 4 pi k. So you could see the only possible solutions are going to be when k is 0 for both of them, because if k is 1, it's going to be outside of 2 pi, and if k is negative 1, for example, that's going to be smaller than 0. So these are actually the only 2 solutions that I have for this problem. So 7 pi over 3 and 11 pi over 3. All right, nice job. Those can take some practice and getting used to, so just be patient with yourself. All right, moving on to some more advanced examples. Find all solutions of each equation in the interval from 0 to 2 pi. So here we have, for example, A, 2 cosine squared x plus 3 cosine of x plus 1 is equal to 0. Now notice this is a quadratic equation, right? So let's see if we can factor it. If we can't factor it, then we have to use the quadratic formula, but hopefully it'll factor. So let's see. 2 cosine x times cosine x would give me 2 cosine squared x. And then the last term's a 1. And both of these should be positive, and I'll get a middle term of 3 cosine x. Yep, that works beautifully. Now I'm going to use the zero product property and set each of the factors equal to 0. So I'm going to set 2 cosine x plus 1 equal to 0, or cosine x plus 1 is equal to 0. Nice. Now from here I'm going to get cosine of x is equal to negative 1/2. So let's think, on the interval from 0 to 2 pi, when is cosine equal to negative 1/2? Well, that would be in quadrant 2 at 2 pi over 3, as well as quadrant 3 at 4 pi over 3. Okay, that takes care of the first equation. Or cosine x is equal to negative 1. Well, where is cosine equal to negative 1? That's at pi. So x is equal to pi. So in this case, I'm going to put all 3 solutions in one solution set. The order that you list them doesn't matter, just as long as they're all in there. So 2 pi over 3, 4 pi over 3, and pi. Come back. Good. Nice job. All right. Next problem, 3 secant squared x times tangent x equals 4 tan x. Did I give a hint already? I said minus. We're going to be setting this equal to 0. The reason why you don't want to start out maybe factoring or dividing or doing something like that is, remember, the property is called the zero product property that we used to solve the previous problem. So your equation has to be equal to 0. You can't work with it when it's written this way, and you never want to divide by a variable or a trig function because you're going to lose solutions to your equation. So set it equal to 0. Let's just separate things here. So we have 3 secant squared x tan x minus 4 tan x is equal to 0. Now, in this case, we can factor still, but it's going to factor differently than the last problem. I'm just going to basically pull out the greatest common factor, which in this case is a tangent x. So I'm just going to factor that out. So I'm going to have tangent x times 3 secant squared x minus 4 is equal to 0. And then from here, I have the equation completely factored and it equals 0, so I can set each factor equal to 0. The zero product property lets me do that. So tan x equals 0, or 3 secant squared x minus 4 is equal to 0. Okay, so let's think here. When is tangent equal to 0? Well, tangent is sine divided by cosine. So anytime sine is 0, tangent is 0. So I'm going to list out 0, pi, and not 2 pi, because notice the interval here does not include 2 pi, but it does include 0. So I stop with those 2 values. Now looking at the other equation, this would mean 3 secant squared x is equal to 4. So secant squared x is equal to 4/3. I'm going to take the square root of both sides. And don't forget, you have to put a plus or minus, which means secant x is equal to plus or minus square root of 4 is 2 over square root of 3. You can leave it like this, or maybe it's a little easier for you to think of this as cosine x equals plus or minus rad 3 over 2. And then now we're going to list every angle that gives us a cosine of either positive or negative rad 3 over 2. So it's everywhere we have a pi over 6 reference angle. So that would be at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Wow, so how many solutions do we have to this equation? We have 6 total. So put them all together in the solution set. 0, pi over 6, 5 pi over 6, 7 pi over 6 and 11 pi over 6. Looks good. Okay, how are we doing? Next example, we have sine squared x equals 5 times the quantity cosine x plus 1. So any ideas how to get started? It's a good idea. Let's distribute the 5 on the right-hand side and then set the equation equal to 0. Okay, so we have sine squared x equals 5 cosine x plus 5. And then I'll subtract 5 cosine x and 5. So I have sine squared x minus 5 cosine x minus 5 is equal to 0. Okay, I can't factor this equation because notice I have a sine squared x and a cosine x. And so what I want to do in this case is see if I can use an identity so that I can rewrite the equation and only use one trig function, meaning not a mix of sines or cosines, but only one of the two. Well, which is the only one I can replace? Remember, our Pythagorean identities involve sine squared, cosine squared, tangent squared, secant squared, etc. So only the squared term gets to be replaced. I'm basically stuck with this equation having a cosine x in it, but I can replace the sine squared x with 1 minus cosine squared x. And then I have minus 5 cosine x minus 5 equals 0. All right? Now let's see here, I can combine like terms, so I have negative cosine squared x minus 5 cosine x minus 4 equals 0. And then let's just multiply the whole equation through by a negative, right? No point in keeping them all with that extra minus sign. So cosine squared x plus 5 cosine x plus 4 equals 0. Beautiful. Now, let's see if this factors. Anytime you have a quadratic equation, try to factor it. So cosine squared x, that's going to be cosine x, and then I need the last term to multiply to 4, but since the middle term has a coefficient of 5, I'm going to use 4 and 1, and both are positive. Okay, things are looking good. Now I can use the zero product property. So this tells me either cosine x plus 1 is 0, or cosine x plus 4 is 0. So solving each of these, first one tells me cosine x is negative 1. Well, when is cosine equal to negative 1? Imagine your unit circle. When is x equal to negative 1? Well, that's at pi radians. Or cosine x is equal to negative 4. Now think of your unit circle. When is cosine equal to negative 4? Never, right? Imagine when we graphed cosine couple chapters ago, the amplitude was 1. So cosine's never bigger than 1 and it's never smaller than negative 1. So it's impossible for cosine to be equal to negative 4. So that equation will not give us any solutions. The only solution I have is pi. That's it. So he's all alone in the solution set, but it's okay. All right. How are we doing? These ones are maybe a little bit easier than the first couple examples, as long as your factoring is pretty good. Okay, example D, we have 2 sine squared theta over 2 equals cosine theta. Again, notice I have a mix of sine squared and cosine theta. And so I want to replace that. And instead of replacing sine squared with a 1 minus cosine squared of the same angle, see how this is theta over 2? Maybe I can use my half angle identity. So remember, sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. And in this equation, I have a sine squared theta over 2. So that means sine squared theta over 2, basically, you just ditch the square root now because we squared both sides. So it's 1 minus cosine theta over 2. So I'm going to substitute this expression here for the entire sine squared theta over 2 in the equation. Now watch how nice it's going to turn out. So I have 2 times 1 minus cosine theta over 2 is equal to cosine theta. All right. And are you noticing something we can do? I can cancel out this 2 here. Ooh, things are turning out nicely. So I just have 1 minus cosine theta equals cosine theta. Add cosine theta to both sides, so 1 equals 2 cosine theta, which means cosine theta is 1/2. All right, cool. So let's think. When is cosine equal to 1/2 on the interval from 0 to 2 pi? Well, theta would have to be in quadrant 1 at pi thirds, or quadrant 4, at 5 pi over 3. So those are the only two solutions. Pi over 3 and 5 pi over 3. All right. Nice job. Last one. So we have 3 cosine squared theta plus sine theta plus 1 equals 0. I want you to take a minute and pause the video and try to solve this one on your own. And I'm going to give you a hint. You're going to need to use an identity, because notice here this is a cosine squared, and here we have sine theta. So I want you to think what identity we would need to use, and then see if you can finish up the problem from here. It's pretty similar to a couple of the ones we just did. So pause the video, work on it, and then I'll continue with the solution right now. All right, so we're going to replace cosine squared theta with 1 minus sine squared theta. So we have 3 times 1 minus sine squared theta plus sine theta plus 1 equals 0. So distributing the 3, now I have 3 minus 3 sine squared theta. Not loving that theta. Felt much better. Plus sine theta plus 1 is 0. So combining like terms, let's see, I'll write it in descending power. So negative 3 sine squared theta plus sine theta plus 4 is 0. Don't ever try to factor when there's a negative in the front like that, okay? So we're going to multiply everything through by negative 1. So 3 sine squared theta minus sine theta minus 4 is 0. All right, can we factor from here? Let's see. So 3 sine theta, and I want my middle term to be negative 1. So this needs to be a 1, this needs to be a 4, yes? Positive, negative. Yep, that checks out. Okay, then using the zero product property, I'm going to have 3 sine theta minus 4 equals 0, or sine theta plus 1 equals 0. And then solving each of these, this would tell me that sine theta is equal to 4/3. Well, when is sine theta equal to 4/3? 4/3 is bigger than 1, so this is not possible. That equation will not give us any solutions. Oh no, what about the other case? So sine theta equals negative 1. Does sine ever equal negative 1? Absolutely. When theta is equal to 3 pi over 2. All right, so that's our only solution, 3 pi over 2. All right, so this concludes the lesson on section 6.2 and 6.3, solving trigonometric equations. So make sure you take your time, review your identities, and work carefully, especially reviewing your factoring when dealing with these problems. Don't forget to comment, like, and subscribe.